Okay, I think we can start. So we're very honored today to have our seminar speaker, who is Xiaochun Li from UCLA. Professor Xiaochun Li is the Raytheon Endowed Chair in Manufacturing Engineering in the Departments of Mechanical and Aerospace Engineering and Material Science and Engineering at UCLA. He's the pioneer and global leader in fundamental studies, scalable manufacturing, successful commercialization, and practical applications of nanotechnology-enabled solidification processing. And he currently serves as the director of the Smart Manufacturing Innovation Center at UCLA under the USACSMII. He received his PhD at Stanford University in 2001 and is the holder of multiple Best Paper Awards and patents, including more than 10 of those licensed and commercialized by industry. Dr. Li received the 2002 National Science Foundation Career Award, 2003 Jury Glusty Award F Award from American Foundry Society. Oh, I meant to say Glusty Outstanding Young Manufacturing Engineering Award from the Society of Manufacturing Engineers in 2008, and he received the Award Taylor Award from the American Foundry Society. Okay, and in 2022, the ASME William Inor Manufacturing Technology Award. Dr. Li was previously a professor at the Department of Mechanical Engineering at University of Wisconsin-Madison from 2001 to 2013. And he served as the director of Nano Engineering Material Processing Center at UW-Madison between 2009 and 2013. Dr. Li has been elected fellow of the National Academy of Inventors in 2021. He's also a fellow of the American Society of Mechanical Engineers and the National Society of Manufacturing. So it's obvious we are honored to have you today, and we will turn it over to Dr. Li to present nanotechnology-enabled large-scale manufacturing of metals for complexity and sustainability.
Thank you. Thank you, Udawak. Yeah, thank you for the introduction. I'm great to be here, right? So like I mentioned, surprise in Michigan is harder than Los Angeles. That's one thing I learned, right? So that's great. But today I talk about, my topic about nanotechnology with casting, mostly in the solidification processing side. So yeah, my talk will talk about different, topics, introduction, and talk about especially nanoparticle dispersion for the mass manufacturing, and then how we use nanoparticle effect for controls, material control, also manufacturing control, and then mention briefly about commercialization and summary. So metals we already know, right? So we cannot live without metals. Although I know people say we cannot live without internet, without AI, but without metal, guys, we are doomed. Right, so metal always here for thousands of years. I still like it. So high performance metal, obviously very important for our life, right? Needless to say, all the electrical, thermal, chemical, almost everything there. So wide range potential application and almost everywhere: electronics, automobile, defense, biomedical, aerospace. So if we from the manufacturing or from metallurgical method point of view, in high level, really, we have developed 4 platforms for our guidance about manufacturing process. Really, about alloying, like steel making, right? Iron, carbon, and we have a lot of plastic deformation. Also, the way how to make small grain can be liquid or solid, right? Or heat treated to cure different properties. So this mostly we learn the 4 platforms to do the work. Right? This has been successful for our human society for thousands of years, especially last 200 years or 150 years. It's very fruitful and successful. But obviously, we also realize the metal became very mature. We take it granted. That's why metal is not sexy anymore. So And certainly we still have some area we want to go better properties. And the one area especially I want to mention is manufacturability, right? A lot of metals we developed as a material scientist, I say 95% of the time, the material is so good, everything great, but they cannot go to that society use because manufacturability problem. You cannot make them massive, you cannot make them low cost enough, right? For that, application. So certainly that, since like 90s, we know the new dimension, I try to bring the metal side and almost bring to every, engineering discipline is nanoscience, right? So, and today we just take it granted. Yeah, we have a lot of nanoscience research almost, by default, all the graduate students or engineers must know. So nanomaterials or nanoscience really, we already know, I will not say too much details. It's increased ratio of the interfacial area to volume, right? So really that intermolecular and interfacial forces will dominate in all the interactions. And they will induce unusual physical, chemical and mechanical properties. And since the 1990s, a lot of research there. Knowledge base start build up mostly for lower temperature chemistry, right? Most of them. High temperature side is scarce, a little bit. So in recent years, obviously we can move more and more to the more harsh environment, technology, right? Their behavior. And I would say practical application is the painful spot when everyone talk to nanoscientists. What do you do? What do you apply to industry? Then a lot of guys, oh, no, I don't know, right? So that's the problem. I would say very slow, relatively. Nanoscience and nanotechnology for industrial application, especially we come to Michigan, guys, we do a massive manufacturing and a lot of nanoscience just say, oh, no, guys, don't talk to me. I'm not talking about massive production. So that's the one really practical application I would say is slowed down. That's why in the last 5 years, nanotechnology is not fancy anymore. Right? A lot of guys actually have some negative impression about nanotechnology because industry just do not get much benefit or enough benefit, right, to that. But I would say that, since 2000 something, they talk about nano manufacturing, right? At that time, the nanoparticle, nanofiber, nanotubes, nanoplanets, very expensive. Today still expensive, but already dropped 10 or 20 times now, right? So my guess, potentially some area we can get to the application domain. So really for the metal guy, I'm one of the few guys, just like Alan. So like metal, right? I hold my lifetime the metal guy somehow. So I stuck with metal, I like metal. So, but what nanotechnology can do in the metal, right? So obviously metal can be liquid form, can be solid form. In the liquid form, I can see that, use nanoparticle to generate so-called nanofluids, like to transfer mostly talk about chemical, thermal storage side, or the battery recent years actually for the sodium, lithium, they're all metallized, right? So how to control the dendrite or some other, that's interesting. But most, I would say, in traditional manufacturing, metallurgy side, it talk about how nanotechnology in solid state, and how to control property. And actual theory about nanotechnology in the metals are well developed. And we already know what the nano can do if we can do it well. So all of us strengthening talk about nanoparticle or nanoplastics, right, to control the strengths. This is well established since the 1930s, maybe, right? So, and then the pinning effect is one of the key effects to control for high temperature, for creep resistance, right, for the high performance there. And of course, recent years, there are a lot so-called, electrical, magnetic, thermoelectric, right? Most dealing with interfacial control using nanoparticles or nanophases. And for me, I'm a manufacturing guy, and really how to, from beginning, I always set the goal for massive production and how to get nano into larger scale manufacturing, right? So one thing is the dream at that time is really, okay, get nanoparticles dispersed into molten metal for casting, for larger scale, like steel making, continuous casting, or permanent mold or high pressure die casting, like that kind of high level. So the key thing is first big if, can we disperse nanoparticle, like into molten metal? It's a big if. I did not know at that time. I was very young, aggressive, and I said, how difficult is that? I buy a high-speed motor, I get nanoparticle in, I stare them. If you say I cannot disperse them, I stare harder. That's my mentality. But after a couple of years study, I found that, whoa, it's not possible, not good. And then we studied physics, everything. It is a very difficult problem. They don't want to talk about more. And of course, even with dispersed nanoparticle there, So still another thing is certification to make products, right? Ideally, we get nanoparticle into the matrix, into grain. But oftentimes you see, when you see the paper in early 2000s, a lot of paper is here, right? To push the grain boundary. Of course, we might think they are negative, but actually today, sometimes we can also utilize the negative side to our advantage. So right now I talk about a key part of my research. Really, this problem, hurt me, dragged me down for 15 years, right? How to get nanoparticle dispersed in molten metal, right? So at the beginning, it seems like very simple problem, right? But turns out a very difficult problem. And then we studied physics, right? The interaction between nanoparticles. Of course, nanotechnology coming along in 1990s, a lot research in the water-based, in polymer-based. They have some successful story. Just like milk in the morning, you put there the self-dispersed. Right? Milk is really nanofruits, right? Nano droplets there, the self-dispersed because they, double layer, that kind of stuff to repel the particles. Like because particles naturally in the nano scale, they will attract to each other by 1 watts attraction. And they will just universal, right? It cannot against that. It's quantum mechanical. But the problem is in the nature is how to make them, they like each other so much, how to make them, hey, keep some distance, personal space. This is a tough one, right? So traditionally, we can use electrostatic or double layer, or in the polymer-based, polymer engineering, they get surface surfactant, basically get standard repulsive force, right, against them to keep space, to dispersion. But unfortunately, in molten metal, this is all difficult. Actually, we have no way to accumulate electrical potential on the surface. But of course, recently, Alan, that student, might have some special thing. I don't know. That's still mystery. So they might have something, I don't know. But generally speaking, in the static that kind of way, you have no way to accumulate the electrical charge there because the molten metal here, the electrons is conducted away, right? Very quickly dilute everything. So this almost none in molten metal cannot do that. In other ways, at molten metal, we talk about high temperature, right? We are not WE guys. WE guys talk about 60 degrees C high temperature. We are talking about 600. Right? And 600, all this surfactant dead and decomposed, right? So that's the thing. So basically, we have no repulsion force. We only have attractive force. And that became very simple physics. Basically, we only have attraction. We have no repulsion. And that's one of the key problems that we form the cluster all the time. It's almost hopeless, right? I spent almost 10 years. I tried everything, mechanical, stirring, acoustic. We get some success, but couldn't get to the production. Once we stop ultrasonic, nanoparticle go back again. So this really, simple but difficult problem, right? So until 2015, we solved the problem by really going to the nanoscience, go physics study. Okay, especially you talk about inorganic high temperature interaction between the nanoparticles in quantum mechanical domain. It's very difficult, actually. It is. Okay. So, but by then we found out, okay, this 2 nanoparticle, we wanted to keep them apart, right? Originally, we thought we need to keep a force. We need to find a force. But later we found out we do not need to find a force. Actually, we just need to find an energy potential to do that. The force is the first derivative of energy, right? So, and once you open up that one, then we study the interaction potential between the nanoparticles. Normally, they're attracting each other by the 1 watts potential, right? So, and this is quantum mechanical factor, like we call Hammett constant, right? So, it's how much they will have quantum mechanical effect, right? Attract to each other in air or in vacuum. And actually, we found out if this 2 nanoparticle, right, if can be close enough, quantum mechanically close enough to molten metal, then these 2 minus each other will reduce this potential significantly. Right? So traditionally, we cannot do that because mostly we choose a nanoparticle in ceramic particle. And the molten metal is metal, right? They just don't like each other. Quantum mechanics is so different until we realize there are some ceramics, like metallic ceramics. They are very stable. They have partial metallic bond. So they can get closer quantum mechanically, and then get closer, we can reduce the 1 watt potential. And once 1 watt potential gets small enough, of course, need to go size, right? And also go, distance a little bit larger than maybe 0.5 nanometer-ish, then we could get this one less than KT. And KT is the symbol like energy, right? Thermal energy, thermodynamic, they are always right to help us to disperse everything. That's exactly what happened in traditional alloying. You put the carbon, solid carbon into molten iron, the self-disperse, right? Of course, the atomic scale, right? But the same, almost similar principle. It's about energy, right? So thermal energy is higher than attraction potential. They get dispersed entropically. And of course, we are against them to go together. Because nanoparticles like twin brothers, they always will go together, sinter together, become the big particles. They have a tendency. So we need to find a way to against them to go back, at least kinetically for a couple hours or days. So this one relates to the energy barrier, right? If the wet well is like nanoparticle wet with molten metal, then they are not easy to get together. So I always make the analogy, it's like you have your close friend in a bar, sports bar. Like you go there, it's very crowded, like all the general public there. If the public is very friendly with you or your friends, when you go there, even you see your best friend in the far corner, you will not quickly go to unite with your friend because you have so many friends to talk to. You need to hang out with other guys. So that's talk about wettability, right? So that one will slow down your unification with another particle. So that's the key. And also, like if this attraction force or potential is small enough, then all this bar, this kind of alcohol, everything will make everything is so dispersed. The same thing. So nanoparticle do the same. If you satisfy wettability, satisfy size, satisfy the like a quantum mechanical that reduction of the attraction, then you can get self-dispersion. Once we realize this principle, then we need to engineer the particle to find the particle, to find the size, right? To find a way, engineering way to get nanoparticle in, and once you get in, they're self-dispersed. So this one of the key we discovered in 2015. And then after we discovered that one, we are open, right? That's where we know we can do scale up production because nanoparticle can be dispersed by themselves. We do not need to force them. So that we use hammer, we use acoustic to hammer them off. They always go back. But I know, hey, we don't need to do anything. Just they will separate by themselves. So this really get nanoparticle dispersed by even low percent, 14%, even 25% or lower percentage right now, right? So even 1%, they separate. So that's good news. And once we have that one, right, so we can do all the manufacturing or microstructure materials control. The first one we talk about that nanoparticle, what it can do, helping us from traditional metrology side or manufacturing side. And the first thing is actually 2005 years, we always find out one thing. We put nanoparticle in, always get a grain refiner, right? So very good, very effective grain refinement, right? So then, and then of course, that before 2015, we didn't do the self-dispersion theory, right? Our dispersion was so good, but nonetheless, the grain refiner always good. But commercially, we couldn't get success because we couldn't get scale up production. And also at that time, nanoparticle is more expensive than conventional grain refiner. We don't have anything, really, revolutionary at that time, like to make that happen. And also we can see why at that time we couldn't break traditional barrier. That without self-dispersion nanoparticles, so conventional that fundamental limit for grain size during casting is governed by this equation. The grain size equal to how much nucleates you can have, and how effective the nucleates, and especially this one, growth restriction. Traditional nucleant theory is dependent on chemistry, right? When you push that solute out, right? They have enriched in the front, they block, like push back, but they have limit. Normally Q about 50K, mostly in the industry. That's why this one size, we didn't get this one, we get larger grain size, right? That's why in traditional casting, normally get hundreds micrometers or tens of micrometers at minimum, really, right? You cannot get better than that a lot of times, unless you go really fast cooling. But when you go very fast cooling, you do not go mass production, right? So this is the dilemma there. And then it's fascinating, right? So that we study how nanoparticle compare the traditional microparticle-based grain refiner, because the most traditional grain refiner is based on, about 1 micrometer to 6 micrometer particles. They're very effective. They already use in industry very effectively, inexpensively, right? So we study nanoparticle compared to the microparticles. We found actually we are not as good as them, because we need a much more undercooling because the smaller size, they need more undercooling to solidify, to grow the solid, right? They, solid in crystal. So on surface, looks like nano cannot win. That's why around 2005, 2008, after the PhD graduate, we think, oh, we quit on this direction because we cannot win. Because this one will win, we need more undercooling, means we need more, right, the processing condition to enable that. So until 2015, we finally solved the self-dispersion, nanoparticle self-dispersion, and we came back to study the nucleation phenomenon. We found surprisingly, we have something really unusual happening here. Actually, we all know if you work on the metal side, how to get nanocrystalline or ultra fine grain, right, in the metal in the production is very difficult. And most guys rely on the fast cooling for thin films, right? For the laser processing, thin film deposition, and all in solid state use severe plastic deformation. But in the production scale, right, in the casting, nobody can do small grains really, like in the larger one. But surprisingly, in 2015, in the copper or pure copper, we put nanoparticle in a few percent. Surprisingly, just use regular casting, like 4 degrees C per second, right? It's quite slow. It's almost like sun casting and the permanent mode, like between that, that kind of production cooling rate. We found, really, really small grain, ultra fine, even nanocrystalline. So this really shocked us, right? Because we thought it's impossible, but right now it's make possible. That, allow us to study why they happen like that. Actually, we find out because more important, right, is about nanoparticle-enabled growth control, basically restriction of the growth. It's not about nucleation. The early days, we always think, hey, people say you have more nanoparticles, you have more nucleates, like grow. No, it's not like that. It's more important. It's not only have growth, the nucleation. More important is once you start grow, they restrict your growth. Because when let's say this grain start to grow, nanoparticle, they just pin down this growth. If you want to grow over, you need more undercooling, right? You see, the nanoparticle, like a 20 nanometer, you need almost 10 degrees C more, right? For undercooling, then you will not grow because you need more weight and for the cooling weight. So this one really almost similar to we have significant restriction factor by nanoparticle. So this is the physical restriction. Unlike traditional methodology, free growth theory by chemical, the method for restriction. And because we have a physical nanoparticle to restrict growth, they're very effective. So by this way, we really can break the fundamental limit of grain refinement in traditional casting methodology. So basically, traditionally, the reason we couldn't get small grain because they stop it here, right? The Q is small. And this one will stop here. Your grain size is dictated by this process. You couldn't realize your full potential. But once with nanoparticles, right, they not only have infinite high Q, physical Q, right, they almost drop here, also have a lot. Nanoparticles allow the nucleation. So you can really potentially go to nanoscale. So this is theory, nanoparticle restriction go to ultrafine grams. And here is difference here. We can see traditional methodology, free growth theory, you have nucleates. Sometimes we use grain refiner into it to make it more nucleates. But once they start grow, they grow so quickly, right? It's naturally so. The free growth theory, I grow, I win, right? So they also release latent heat. They will kill all the nearby competitors, right? The nearby competitors will smashed away by this released latent heat. So they just become big grain. But in the nanotechnology, first of all, of course, we need to rely on the nanoparticle self-dispersion there. Once you disperse well, at the beginning, the first wave, you have some nanoparticle nucleate grains, right? Some big ones, some small ones, the nucleate. But they want to grow, the nearby nanoparticle pin them down, right? They block you. They cannot allow you to grow. It's almost like in freeway, you allow the biking guys, the e-bike guys go to the freeway and they say, don't kill these guys, they have same right like you. No matter how high speed car you have, you need to slow down, right? So this exactly happened. It's almost like socialism. Like this is truly socialism, I tell you, right? It's blocked, and then the nearby the poor guy say, oh, it's my opportunity to grow now, and block you again, and then grow again and block you again. So it's like continuous nucleation, continuous growth restriction. This is way different from traditional methodology. Traditional methodology is one shot, I win, Once I win, I grow very quickly, occupy my space as much as possible. That's exactly why we couldn't get small grain, right? Unless you use laser cooling and everything, otherwise you cannot get it. But right now, use this technology, we can go very slow cooling rate because nano doing the work, right? The pin you down. In social reason, allow you continuously block you, and we can get very small grain. And once with that one, we further go in deeper in what we can do in the manufacturing side, in certification processing. Actually, we found out more. Like when we have nanoparticle during certification, actually, we can also enable effective liquid backfeeding. Right? So very traditionally have the liquid, the dendrite, you can think about. Previously, the dendrite stuff, the block liquid here, that's the key for hard cracking, right? But right now, with nanoparticle, they're all globular, very small uniform, they do not have the issue like traditional hard cracking. And also they refine both primary and secondary, and they increase terminal liquid fraction. That's exactly the reason we do not have hard cracking issue anymore. Right? This is one of the big discovery for nanotechnology. And also you make the uniform, the secondary phase more uniform distributed. So this make our mass production much more desirable. You do not need as much time to solve the segregation issue for big scale production. So here I go to the manufacturing, right? So really after years research, instead we focus on, strengthening effect because 2000-something to 2010, most of my research focused on how to get stronger metal, how to get better metal. But after 2010, 2015, we most focus on how nanoparticle, right, to change the phase, to control microstructure, and to enable manufacturability of traditional impassible alloys. So that's the one. So nanoparticle really can help enhance nucleation, restrict grain growth, and modify secondary phase in one shot. Traditional metallurgy, you need almost 2 or 3 methods to do that, to realize 3 functions together. But we can do it in one shot using nanoparticle, and to get unusual control of microstructure and phases. We can get a homogeneous grain structure, and then get enhanced property. And especially here is a new one. I would say our niche here. Nanoparticle enhance hard processability and then manufacturability. So we'll go to detailed application. For example, take aluminum alloys. Aluminum alloys divided into 2 big categories. One's casting alloy, one's powder alloy. Right, for a reason, because casting alloys normally, right, you want the complex shapes, but cheaper, right? Production cheaper. Loud alloy, we want high performance, aerospace, and the vehicles a lot, high performance. They are not use the same method, right? Casting alloys use solidification processing, liquid, right? Loud alloys use plastic deformation and they use machining, right, to get geometry, to get properties. So this one you can compare the strength, ductility, conductivity, including thermal, and also like electrical. The loud alloy all win. So only thing you can see the loud alloy you cannot win is castability, right? So it's difficult, but other surface quality, especially this one, this one aspect I mentioned, anodizing, anodization for all the cosmetic application. For example, Apple guys very good product, beautiful product because the anodizing, right, make colors appealing. Right? So normally loud alloy is doing good, cast alloy is very poor, right? So we can see loud alloy is really desirable, but a lot of times because they're more expensive, right? People go to the casting alloy for shapes, for low cost. So what if we use nanoparticle, right, nanotechnology to unify them, right? Basically, we're casting loud alloys, right? So this is the area we want to go, right? So basically, take advantage of the shapes, also, right? The performance of loud alloys. And to be fair, like people spend decades to work on this area, like try to unify these 2 together, but difficult to solve the hard cracking manufacturability problem, and nano provide a new method. High performance loud alloys in vehicles, a lot 6,000, 5,000 series, right? And also aerospace, a lot 7,000 and 2,000 series. It's the high performance, high strength, that weight ratio, and exceptional mechanical properties. But unfortunately, normally they are not good for casting. They must go California shaping. But of course, we do that because we have no choice. But I would guess if you have choice, you want to do casting of this, that will be very fast, efficiency high and low cost. So this is the way, can we do manufacturing like in the casting way for the loud aluminum alloys? So certainly we already identified the problem difficult, if not impossible, to cast the complex geometries in that 2,000, 6,000, 7,000, or 5,000, even 3,000. Right? So for that, so and they really have energy intensive extrusion loading process and energy consuming machining for shapes, and a lot of metal waste for sure, right? And they're also much more expensive, actually, right? Because it's not because of material in some way. And material might be similar cost, but really it's about manufacturing cost, right? How to make manufacturing that feasible and low cost. So traditionally, of course, some area weldable, but a lot of area is like 2,000, 7,000, not weldable, and also low thermal stability. So here, why loaded alloys, aluminum alloy is difficult for casting? Its number one killer is hard cracking susceptibility. It's because during solidification, like we mentioned, traditional methodology is you have a dendrized growth, right? They quickly occupy space, and then they encircle the liquid, right? In the solid phase. And the liquid have no way to backfeeding, no way to like compensate for the shrinkage depth. Then they have hard cracking there. Like a lot of hard cracking, or you have a huge grain like growth there. So this problem is really the contraction and also the nucleation behavior. And also have porosity issue, right? Then they have hydrogen bubbles during the casting for loaded aluminum alloys. And nanoparticle really can solve the problem quite well, right? So nanoparticle, for example, here we always have equiax, right? Also have globular grain, and then they always grow very slowly, gradually. So their solidification zone, like a latent heat zone, they're a little longer than convex because the nuclei grow slower, allow us during the latent state, right, much longer time for liquid to penetrate, backfeed. So by this way, we can really solve the problem, and even with low percentage, and that's good for industry guys, right? So lower cost, lower percentage, better economics. So we found out, fortunately, that even like 1.2%-ish nanoparticle can do very well, better fluidity. That means the liquid metal can flow much better, and especially eliminate hard cracks. And also enable processing traditional impossible, like a 66-1, by 114, 775, you cannot cast them. I know with nano, we can cast them easily. And here is the first one that nanotechnology-enabled casting 775. 775 is aerospace alloy, the highest strength in commercial like domain for aluminum alloy. This normally is very difficult to manufacture. Generally speaking, aerospace industry, they talk about fly to use ratio, right? So talk about 10-1. Means you buy 10 kilo, you only use 1 kilo to go to sky, right? 9 kilo is all machine off. So this really costly process. But right now you can see we can cast them directly, right? This shape. Traditionally, you need a 5-axis, the ML, CNC milling stuff to do that. But right now, in one cast, we can get geometry. And also because of nanoparticles, we can get grain size very slow cooling, very small grain. And even other T6 grain size still very small, right? So by this way, first time, we can do aerospace LOE, can do the casting, right? Like that. Solving the manufacturing issue, lower the cost, no hard cracking, and easy to cast the complex shapes. And by this way, reduce also small grain, everything, reduce stress corrosion, and especially reduce buy-to-fly ratio by 10 times. Basically, you reduce our raw material might be more costly than the original 775, but the manufacturing cost, we are 10 times less than traditional manufacturing. So that's where we win. It's more like a nanotechnology-enabled manufacturing of the alloy, right? So, and here is another massive production. Because I'm a manufacturing guy, I'm always looking for massive, big scale manufacturing. After we get self-dispersion nanoparticles, right, then we can do big scale for tons, right? Because high speed, this kind of high pressure die casting, almost like a 20 or 30 seconds make one components. That's where they, of course, for Tesla guys, make a gigapress, right? To make a whole car body in one shot, that take minutes. But this is a very efficient, low-cost way to make complex geometry, larger scale structure, and simple structures. Right? You have multi-metal feeding here, and quickly eject into it in the meters per second, very high speed, like ejection. And they talk about cooling rate, about welding cooling rate, 100 degrees C per second. And then we have the machine can be 80 to 8,000 tons. And today they go to more than 10,000 tons now, right? And that's a machine. Very high speed, very highly automated. A lot of consumer electronics, automobile industry rely on this process a lot, right? To make low cost and high performance, that kind of like components. Especially focus on the aluminum, zinc, magnesium, and copper alloys. And the high pressure die casting is quite rapid growth, like industry, right? Because more and more components were produced by high pressure die casting. Even go larger scale, like Tesla guys, right? Go to the gig, they kind of like get their press. So all this one is really for shooting automobile, electrical, electronics, and cookware, everything, right? Still about 8% annual growth. And here, traditionally, we have problem for high pressure die casting, high performance aluminum alloys, like loud alloys, 66-1, 2024-775. You cannot do the high pressure die casting because hard cracks will kill them. And people tried, okay? It's not like people not trying for a lot of time. That's cracking like crazy. You couldn't solve the problem. And also poor fluidity because they couldn't flow well, right? And also they have a lot, shrinkage, gas velocities. But with our nanotechnology, right, enable mass manufacturing by certification, we solve the problem, right? We eliminate this and they enhance this and they mostly distribute that and also eliminate that. So all this come together, we put here. So really like nanotechnology combined with loud aluminum alloys and combined with mass production like high pressure die casting or squeeze casting is another type of high pressure die casting. So combined together, we can make mass production of aluminum components. And even make anodizing components. So here is some of the products we produce, not in my research lab, but more in my company, Metali, right? So this commercialized all the products. You can see we can produce that nanotech-enabled. Traditionally, it's impossible use this alloy to make the components and also make anodized colorful product there. So this one, friend, and this one I mentioned, this for electric vehicle control. Right? So traditional that gasoline that vehicles might be, we only have maybe $200 something for control, for the thermal control stuff. But for the EV, right, normally today, they mostly talk about $1,000 to $1,500 control units to control the battery temperature, to control the motor, control all the, systems, right? Air conditioning, everything. So this is multiple channels, right? So we'll seal and get liquid to cool. And obviously, we're communication box. And this one is talk about optical module, right, for the high thermal management in small volume, almost like USB. They can flash drive this size, but with 800 or 1 gig, like the bytes per second data transmission by laser, a lot of heat there. And of course, this car camera for the autonomous vehicle, right? So this one talk about like 10 billion parts, right? Worldwide like that. But of course, this one is not so good as ashtray. Like a lot in US, not popular, but in Asia, there's still some quite an ashtray, the colorful product. Here is like another high pressure, squeeze casting, right? So we can get e-bikes, right? Make bike, motor box and the motor bracket. The motor bracket is 775, 661, 2024, and the when wheel and the hard disk. Like for this kind of computer, the technology, and also WAF terminal, and also battery cover, right? We commercialize this one for battery cover, especially with this thermal conductivity in the 6,000 series, 66.3. Thermal conductivity is one of the highest among the commercial aluminum alloys. But traditionally, we cannot do casting. We must do forging and machining, very costly. So today we can go that much cheaper and much more complex geometries. So with that, we can see the benefit of nanotech enabled high pressure die casting, right? So we enable massive casting, right? Day in, day out, right? For that complex parts with complex geometry, all high performance loud aluminum alloys, right? So we really enable much wider material choice for the mass production. And then we almost, I would say, completely eliminate hard cracks. This is one of the big killer for traditional alloys. And also almost complete eliminate gas bubbles. This allows us the die casting component can be welded, right? Can be joined together. Traditionally, the high pressure die casting component is very difficult to weld because there are a lot of bubbles inside. Once you weld, the bubble just come out, right? They create defects. Right now we can do that. And also superior, right? The grain size and fine microstructure and properties, tensile, ductility, thermal stability. Surprisingly, the fatigue life, we get enhanced a lot. That's one thing 10 years ago, we do not believe it. Nobody believe it. Most people think, oh, you put a nanoparticle in heterogeneous particle, you will reduce fatigue life. But actually, in recent years, we found that we enhance fatigue significantly. It's because nanoparticle block the crack initiation, also block the penetration. Right? So that's surprising effect. But anyway, also, to working with the big companies, right? Especially for the cosmetic consumer electronics domain, right? So we found we need colors. I need all this kind of different color to match all this industrial product. And this is all by anodizing. And traditional casting alloy cannot do that because you have too much silicon. They will not get the color out. But right now we use loud alloy, you don't have the silicon there to block you. You can make all the colors out. So this is one of the biggest area, fast growth area for our application. Of course, I quickly move on to another certification application, right? You talk about welding. Like naturally, we solve the casting problem. We know, okay, we do the high pressure die casting. We have cooling rate about 100 degrees C per second, and welding is exactly in the domain, in about 100 degrees C per second, the arc welding. So we also commercialized, right? Put this wire, manufacture that, scale up production. Because right now we can produce nanoparticle dispersing molten metal in big scale. So we can make all kinds of manufacturing, no problem. We make wires, rods, right? So this nanoparticle dispersed there. We can really weld alloy traditionally impossible to weld, such as like aerospace alloy, 7,000, 2,000 series, right? We are the first one in the world, right? To make that in research, also very quickly go to industry. Actually, this one, we go to 65 countries already. Right? So this kind of welding technology for the welding and the additive manufacturing, right? We can also weld the traditional impossible, like two combination, dissimilar welding, like 5,000 to 2,000, right? You cannot weld them. Right now we can weld it together. So this is good about nanotechnology. And here, that really nanoparticle, you can see that without nanoparticle is always have have continuous phase there, and also have a lot of hard cracking stuff. And with nanoparticle, much more dispersed. So by this way that we can really eliminate hard cracking, and also to make that performance much better. And also because we use the same filler metal. For example, in the automobile industry, mostly we want to use 661 or 5083. So we must use dissimilar welded rods, different chemistry to avoid the hard cracking during welding. Right? So you shift the chemistry away to safe zone. And by that, you pay the penalty of the strengths. Right? Normally, strength reduction almost go to 30% sacrifice, penalty. Right? But with our sand composition, that if we go to heat treatment, we can recover 100%. So this is the one thing for the welding. And also, obviously, in the sand, almost like twin brothers. You can do welding, you can do additive manufacturing. So the wire arc additive manufacturing, obviously, we know is high deposition rate, 10 or 20 times faster than powder bed. They can mess up. And the material efficiency, almost 95%, something like that. And they print the largest scale structure, especially for the automobile, for the aerospace industry, for the large single structures. That's great. But the problem for the traditional WAM process is inhomogeneous and coarse grain structure. Like without nanoparticle, always like that. And the anisotropic, like heterogeneous, like mechanical property, and the expect distortion, and they reduce just huge, and surface roughness and dimension accuracies are poor. But with our nanoparticles, with our nanotechnology, right, we can really completely eliminate hard cracks. There's no problem. And no matter how thick layer you build up, nanoparticle always control the grain to equiax fine grain and almost dendrite free. So for us, we don't care about how many layers you build up. We don't worry about dendrite. We do not worry about columnar growth, right, because nanoparticle block them. And also printed parts can have a high performance. And they really significant reduction in porosity and also deformation of print parts. So I will not go to details. The reason we also can control residual stress and distortion. We just have a student defend the thesis 2 weeks ago. So to understand why nano solidification reduce that, because their solidification behavior difference. You can see TIG welding based, MIG welding based, you can do 775 or the structure stuff. And obviously, I won't show you the 775 because a lot of people want 775 high strength. You see, the wire-based deposition, TIG-based deposition, we can get almost go to 600 megapascal with about 10% ductility. This is superb property after the WAM processing. And especially you can see 12 layers from bottom up. 12 layers grain size about 20 micrometers without any change. Right? This is unthinkable in traditional methodology, right? You just cannot control grain size from bottom up the same. But because nanoparticle there, they control very effectively. And of course, that a lot of guys go to the the AM additive manufacturing powder bed one, right? So then I at the beginning I resisted because my PhD thesis 20-some years ago was in powder bed and also DED. I thought I'm done with that, but they after 2012, everybody said, hey, let's do that. So okay, I still came back to do again. So and with nanotechnology this time. So nanotechnology-enabled AM, fusion-based AM is a powder bed in a different way. So you have LOE design with additive manufacturing, laser-based, and nanomaterial design. Altogether, we control the synth to make traditional impossible LOE like 775, 2024, 661, right? Do that. And this is just a manufacturing method, right? To control the energy input. And here we can produce ingot. So basically all technology go back to our nanoparticle dispersion capability for massive ingot production. Once we have ingot, we just send the ingot to gas atomizer, right? They can gas atomize the powder like this. And this one already have nanoparticle embedded inside, right? And with this one, we already have microparticle 775 with nanoparticle inside, about 1% titanium carbide nanoparticles. And then recent years, we still, polishing this paper, right? You can see the properties we can get, really different conditions as printed. We can go to 600 megapascal, about 8% ductility. Go to T6, we can go to almost 800 megapascal. It's much better than a lot titanium alloy. I mean, specific strength side. And also to the hip, because it get rid of cyclic porosity, we can get 16% ductility. If hip plus T6, we can get about 9% ductility and with 700 megapascal. This is probably really, really high, okay, compared to any other aluminum, even to stainless steel, right? You cannot compete with this property. So that shows nanoparticle not only solve that, like the manufacturability problem, also enhance the property significantly, especially combined with laser processing. And here I summarize it, right? So nanotech enabled metals manufacturing. So really good is massive manufacturing of complex geometries, right? Complex part structures, and also create exciting new space, new manufacturing space for high performance metals, like loud alloys. Like recent years, we also go to high temperature metals like steel, nickel alloys, super alloys, right? Go to that direction. The same principle, nanotechnology, like control the microstructure, control the phase change, control that solidification behavior, and can offer very high performance for sustainability. For example, we can really reduce the cost a lot for a lot of consumer electronic components. Because traditionally, we rely on machining, forging and machining to do that. Right? So right now, we can do one shot. So this nanotech methodology or nanotech enabled manufacturing really start with the nanoparticles or nano elements, fabrication and production. I talk about production, talk massive, low cost. And then go to nanoparticle, how to mix, how to disperse in molten metal, and go to solidification, different technology, casting, welding, and deposition or anything, right? With the process and go to post-processing. Heat treat, extrusion, loading, machining, joining, right? For all this kind of process there. So good thing about this is seamlessly, combined with traditional manufacturing, right? This was the beginning. That 20-some years ago, I told myself, I want to do massive manufacturing with new nanotechnology. Right, so that was my the goal 20-some years ago. I'm glad today really they come along, right, for that purpose. And then finally, of course, just briefly, I know we are at the university, we're supposed to not say much, but hey, just talk about real application, right? So I found that MetaD after I solve the nanoparticle dispersion problem. And then right now, really, we say cast and castable, right? Welded and weldable, print and printable. So some products here, right? Like we mentioned, our product in mass production also go to worldwide, right? For these applications. So here, just summarize it. I think number one, the contribution so far, my research and engineering practice is overcome long-standing problem for dispersing nanoparticle into molten metal, right, by self-dispersion and stabilization. So nanoparticle is really effective to breaking metallurgical barrier and the manufacturability barrier in the traditional sense, enable us to have unusual microstructure control, processing, and manufacturability. Right? So on this new pathway, nanotechnology-enabled mass manufacturing of complex metal parts and structure can really enhance our performance and enhance sustainability, right? So, and the successful industrial application for casting, welding, and additive manufacturing is going on the way, right? Also, this methodology, right, can go to all kinds of metals, basically. Not only aluminum, can do copper, magnesium, zinc alloys, right? So, yeah, with that, thank you. Taking me 50 minutes. Perfect. Okay, thank you.
Any questions?
You tried it in titanium.
I tried 2 years, 1.5 years, but I had a problem with nanoparticle stability. I can disperse them, but they react away. So I think I will go back to that direction, especially titanium alumni. Titanium alumni, we know the property is great, but just couldn't do manufacturing well. So that one is really the next phase I want to do.
Even oxide particles were dissolving, or
yeah, nanoparticle, the oxide will not dissolving, but they cannot disperse because based on the theory, they cannot do that. But like today we talk about that we have a new secret weapon come up, right, to disperse the oxide there. So that is another domain. Go to high temperature, right? Go to tungsten alloy, go to nickel alloy. So this next phase of my research, how to get stable, unwettable, right, nanoparticle dispersed in molten metal. So that's another domain. Yeah, we're getting there with another method. Yeah.
Thank you, Dr. Li. So I have two questions. The first question is that when you say you are casting the uncastable,
yeah,
right? And then you show how maybe you talk about it, but I just didn't get it. Have you compared your casted product, the mechanical property, with the conventional rod product, the mechanical property?
Yeah, we have to compare because we need at least similar or beat them, right? You can see our high pressure die casting, for example, 66.1 or 66.3, we are better than loud product. The reason is first, we eliminate defects there. Second reason, because we have the nano control the microstructure much better than loud product. Loud product, normally they rely on the plastic deformation, squeeze them, right? Very good in one dimension, you have very good grain and the dynamic liquidization. But our all, right, three-dimensional, you're not as good as casting one. Traditionally, casting is weaker than loud because you cannot control gravity, you cannot control effects so well. Nano can do that. Actually, we had all to compete with loud alloys. We are better than them. So that's why our die casting product is better than loud product there. So this, and we are cost much lower, right, than other guys. I guarantee my customers, I say from my company side, right? So we guarantee you 10% reduction in your cost. In more than 10%, then we need to negotiate. depend on business. Yeah.
Okay, I have a second question. So I'm very interested in the theory that you talk about how the nanoparticles restricting the dendritic growth and keep everything acquiesced, right?
Yeah.
I mean, is this a theory or you have some evidence to prove this process?
Yes, let me be careful. We have most indirect evidence to show that. We do not have direct evidence.
Okay.
That's why I try to work with Alan to get real neutron, right? To see how the nanoparticle restrict growth. But unfortunately, even with the neutron, that the speed of the nucleation and also growth, the nanoparticle is so small. we almost need a 10 nanometer resolution in X-ray in the real time. So this part we still, try to get there. But indirectly, right, by thermal analysis, microstructure analysis, right, we have that evidence. So basically that we can see the nanoparticle like pin down the grain boundary. And also we found that the nanoparticle allow us to release latent heat very gradually. Traditionally, you see the nucleation is one shot, right? You nucleate latent heat very rapidly, quickly, and then solidify, right? For our process, we are like more like, very gradual release. That because continuous nucleation, that nucleate multiple events. It's almost you have multiple time nucleation events. Traditional free growth theory, you have no multiple, you have one time.
Okay.
Of course, you can have multiple particles to nucleate in one shot, or you have less particles to use one shot. You only one shot opportunity. You win, you win. You don't win, you stop.
Yeah.
But the nanoparticle, this one is like a multiple chance. Socialism, right? So it's almost you're rich, you buy house first, but stop, don't buy second house. The second guy, I'm a lower income, buy house there, and the second guy buy house here, like that. So that's the way we can see the, actually we have one I didn't show here, maybe. You can see the heat release that we get evidence like this. For example, heat release, right? With nanoparticle release very gradual. Without nanoparticle, very rapid, because that's natural. Right, natural free growth is like that. So I win, I quickly release latent heat, kill all the competitors, I win. Right, I occupy as much space as possible. The grain, dendrite grow, right? But the nano stuff, they don't allow you to go there. You only allow it slowly. And that's exactly the key scientific reason we eliminate hard cracking. Right? Because latent heat is very gradual release and liquid continue flow. So like that.
Okay, great.
So that's the reason.
Thank you so much.
Thank you.
This is so cool.
This is the new one, really. It's a physical based, right? It's physical based restriction growth. Traditionally, all chemistry based. You based on chemistry solute enrichment to block the growth. That's why you don't. But the atoms free and they move so fast, diffusivity so high in liquid state. But nanoparticles don't move very fast. They're almost like biking guys in the highway, right? Compared to the cars. That's actually. You could originally we treat that as weakness, but right now in this case is advantages, right? You slow down like that.
Okay, next thank you, speaker.
Then, I'm gonna introduce you.
Thanks.